Okay, welcome to lecture. We're going to continue on where we left off, chapter 17, I think. We'll get started here in just a second or so. Okay, so we've been talking chapter 17, and we've switched gears a little bit and started talking about really thermodynamics. And remember that basically thermodynamics deals with the idea of whether or not a reaction will sort of occur spontaneously. And that's a lot of what we will sort of be talking about in this chapter here, is that idea of spontaneity. And as we talked about last time, remember that if a reaction is spontaneous, it doesn't necessarily mean that it occurs like boom, super fast it's going to occur. It just means, again, under those conditions, um, that reaction should take place. And it may take place really fast, it may take place really slow. But again, if it's spontaneous, what it means is as it's written, it should take place. Again, we don't really deal with how fast or slow a reaction takes place with here. We do deal with that when we talk about kinetics, which again, we'll talk about a lot more in the last chapter, I think, that we cover here in this class. But here again, spontaneity has to do with whether or not that reaction will take place. Now, there's a couple of thermodynamic sort of values that we've seen that can kind of help us along our sort of journey in deciding whether or not a reaction will take place or not. And again, one that we were familiar with probably coming into the class was enthalpy, delta H, which is sort of the heat of the reaction. And again, that basically will tell you whether or not overall, for example, a reaction is endothermic or exothermic. And as we saw and talked a little bit about previously last time, that just being exothermic, for example, doesn't necessarily mean that the reaction will be spontaneous. And just because you're endothermic doesn't mean that it will not be spontaneous. So we saw a couple of processes last time where like two of them were exothermic and they were spontaneous processes that occur. We also saw a couple of processes there that were endothermic, like melting an ice cube, for example. Although that's endothermic, is still a spontaneous process that occurs. So as we talked about, using enthalpy delta H alone as sort of your overwhelming factor of determining spontaneity is not really your best choice. So we do want to look at some other sort of options here. And we started talking about entropy, which is delta S. And entropy is basically the amount of disorder that's happening. So entropy is really a measure of disorder in a system. And unlike certain things, if we do see an increase in the amount of disorder, we actually will see an increase in the entropy. And a little bit different for most people in terms of sort of wrapping around positives and negatives. What that means is we see an increase in the entropy or an increase in the disorder, the delta S value will actually become more positive. So in terms of entropy, more positive is sort of the number that we associate with that process increasing. If we're creating a lot more order, which means our disorder is decreasing, we see the opposite is true where we have a more negative delta S value. So we did some examples here, which I think is where we left off. Again, just kind of quickly going through these again, just to remind you, if we're going through condensation, again, we're going from gas back to liquid. And that's a very good place where you can kind of see the differences in entropy. As obviously in the solid state, everybody is very much more organized or ordered. And as you go from liquid, a lot more room for movement. As you go to gases, right, they're just flying around and things like that. So there's an increase in entropy as you go from solid to liquid to gas. So in this case, we're going from gas back to liquid. We're creating more order, less disorder, and we would expect a negative delta S for that guy. When we form a crystal, again, if you form a crystal, that's pretty much like a perfect sort of solid. Usually only one way that you could kind of do that. And that would also decrease the entropy. That's a very ordered type of situation. Increasing the temperature, like what we had in C, obviously when the gas molecules are at a higher temperature, is going to create more energy, especially with gas molecules, right? Going to be flying around a lot faster, creating a lot more disorder, and we would see that positive sort of increase in the entropy value. And sublimation is that process where we do go from solid, which again is very ordered, to gas, where again everybody's flying around, to a lot more disorder. We also saw sort of a relationship. I don't know how much of that one we'll sort of get into, but not really too much, I think. But that was sort of the Boltzmann relationship there with entropy, where it's equal to basically the Boltzmann constant times the natural log of W, which is the number of microstates. So remember that sort of number of microstates, sort of different ways you could accomplish something. So I think we saw kind of circles and boxes. And again, if there's a lot of different ways that you could sort of accomplish something, then that is more probable of an event to sort of occur and would have a higher entropy value, where if there's only a few different ways to sort of do something, it's going to have a smaller entropy value. All right, so let's get a little bit more into entropy. And entropy really is a state function. And just a reminder about state functions. State functions are really properties that don't really depend on path. What's really important in terms of sort of state functions is sort of where you started and where you ended up. And things like energy, enthalpy, pressure, volume, temperature, and entropy, these are all state functions. So this is kind of the idea behind as well, like Hess's law, if you remember that from first semester, where he took all those individual sort of reactions and sort of put them together to get an overall reaction. Again, it doesn't matter if it happens sort of in one step, two steps, three steps. What's really important in things that are state functions, where you started and where you ended. And that's why in a lot of things that are state functions, we do final minus initial, right? So final minus initial. In a reaction, that's products minus reactants, right? Final state minus initial state. And again, that's typically the most important thing. Potential energy, again, is an example of that. In this picture here, these two guys on the top, they do possess really the same potential energy because of their position. And it doesn't really matter that the blue guy, the blue path there, took kind of the direct path up the hill. And the red guy doesn't really matter either. He cut the more scenic route around the hill. But in the end, they basically ended up in the same position. And again, they have, in this case, sort of the same potential energy. They really started and ended in the same spot, even though one sort of took a alternative path. And again, that's sort of the idea, like what you probably did with like Hess's law, where again, maybe you could build this reaction in two reactions, or maybe it takes three equations to build this reaction. But the overall reaction is just really where you began and where you ended. Now, here are some values for entropy from a table. You have obviously a similar table in your book. In the back of the book, there's usually a pretty big thermodynamic table, usually. But a couple of things that's important about entropy values, delta S values, and since we were talking a little bit about our delta H as well, is units. So in terms of units, we're usually looking at kilojoules for delta H. In terms of units for delta S, it's usually joules. So there is sort of this difference in terms of units that happens when we have these two different values here. And that really does sort of come into play a little later on in this chapter. We're actually going to see a formula that uses both of those values together. So you do need to do usually some type of conversion when you're using those values together, either make the joules into kilojoules or kilojoules into joules, whichever way you need to go to sort of do that. So later on, we'll see one that kind of uses both of those values together in the same formula. The other sort of important difference that you typically will see in terms of delta S and delta H values when you look them up on tables. Delta S, for the most part, is all positive values. And unlike delta H, when you have something, say, like O2 H to things in their standard state. As you may remember, delta H values for these guys are typically 0, right? And unlike that, though, for delta S, you actually will find values in tables for that. So I think here, some of those values over here. So unlike things in sort of their standard state or natural state for delta H, where typically it's a 0 in terms of the value, you will actually find entropy values when you look them up in the table. Just also a reminder, you will have to go to a table for certain problems, obviously, or use a table. A couple important things to remember when you do go to, say, a thermodynamic table. A, the units are important, obviously, but B, also important is to look up the value for the correct state. So, for example, something like water, you typically will find 3 values. One in the solid state, one in the liquid state, and one in the gas state. And other substances as well in these thermodynamic tables also are very similar. You'll see different values for different states. So not only important to find what you're looking for, but B, make sure you find what you're looking for in the correct state so you use the right number. So let's talk a little bit about the laws of thermodynamics, most of which were sort of talked about a couple of times here. But the first one is, maybe if you weren't sure, but the first law of thermodynamics is really that conservation of energy. So you probably talked about that, obviously, when you talked about enthalpy and probably specific heat chapter, whatever chapter that energy chapter was in. But the first law of thermodynamics really is that energy can be converted from one form to the next, but we don't create nor destroy energy. And there's really sort of in terms of energy and a lot of things that sort of relates to this as well, right? There's really a lot of times 2 things that we look at. There's the system, and then there's the surroundings, right? So you have the system, you have the surroundings. And in terms of energy, for example, because we don't lose any energy along the way, if the system loses a certain amount of energy, which would be negative for the system, the surroundings will gain the exact same amount of energy. It would just be positive in terms of the surroundings. So if the system lost 40 joules of energy, it would be negative 40 for the system, but the surroundings then would pick up 40 joules of energy. That would be a positive number because it would be endothermic for them. So a lot of what we look at in this chapter really does deal with those 2 sort of aspects of it, the system and the surrounding. A lot of times the system that we deal with usually, right, are usually the reactions, right? So sometimes instead of, say, delta S of the system, you may see somebody say delta S of the reaction, or even delta H of the reaction instead of delta H of the system. And that's usually what we're interested in, is some type of reaction. So the system for us a lot of times could be a beaker, could be a test tube, could be wherever you're sort of doing that reaction. And then obviously the surroundings is everything outside of that area. Now, the second law of thermodynamics is what we're sort of talking about here with entropy. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So one way that we could use entropy to actually calculate whether or not a reaction will be spontaneous is we do have to calculate what is known as the delta S of the universe. And the delta S of the universe is basically made up of 2 things: the delta S of the system, which a lot of times is the reaction, plus the delta S of the surroundings. Now, if you calculate the delta S of the universe and you get a positive number, then that reaction is going to be spontaneous under those particular conditions. Again, doesn't necessarily mean that the reaction occurs super fast. It just means that that reaction should occur. If you calculate the delta S of the universe and it's negative, it means that reaction would be non-spontaneous in that particular situation. And obviously the reaction would not occur the way it is written. If you happen to calculate delta S of the universe and it equals 0, then the system is at equilibrium and there really is not going to be spontaneous heading to the products or reactants. It's going to kind of maintain where it's at, right? Basically what equilibrium means. Everything's going sort of back and forth at the same rate. So we'll be able to maintain where it is kind of in terms of a reaction, not going to head one way or the other in that particular reaction. So individually, the system, the delta S of the system and the delta S of the surroundings, we're going to talk about how to actually calculate each of those in just a second. But individually, they really will not necessarily tell you if the reaction is going to be spontaneous or not. You do have to sort of calculate that delta S of the universe to sort of determine that. So let's just talk about then one process, or a very common process, to calculate the delta S of the system or the reaction. And essentially is very much like how you would calculate the delta H of a reaction. Is we basically want to take all of the delta S values we would find in the table for our products. We also want to make sure that we multiply by the coefficients in the balanced equation, because those are technically the moles. And then we want to subtract it from all of the reactant delta S's. So again, this is when we're talking sort of about state functions, this is like our final state, right? And our initial state. So basically we're taking final minus our initial over here and figuring out the change in entropy. This is what this means. This is the change in entropy. The little knot that you typically will see in thermodynamic sort of values usually indicates that the reaction was done under what is referred to basically as standard conditions. So for the most part, what that means is when you see that little knot symbol, you usually will get those values kind of from a table. And most tables that you look up these values, like the table we just saw, are again the table that you would find in the back of your book, are usually done under what are sometimes referred to as standard conditions. And standard conditions pretty much means if we're talking about pressures, the pressure would be 1 atmosphere. If we're talking about temperature, the temperature would be 25 degrees Celsius. And if you happen to be talking about concentration, usually that means 1 molar as well. So most table values that you look up, those are usually the conditions that you're dealing with. 1 molar, 1 atmosphere per pressure. Temperature is 25 degrees Celsius. And again, the concentration is 1 molar. So if you are just given a reaction, kind of like what we have here on the example there, and that's all you're given, and you're asked to calculate the delta S for it, pretty much what that means is you should go to a thermodynamic table and find the delta S values for everybody, do products minus reactants. So why don't we try one? And obviously you don't have a table, but if you went to the table, these would be the values that you would find. So why don't you calculate the standard entropy change, which is basically in words what this means, where it says standard entropy change is basically that. So why don't you see what you come up with, and then we will talk about it. Okay, so let's take a look at it here. So again, these values here, if they're not supplied to you, which they may not be, they obviously would be in a table. you would look up these values. Again, you would want to make sure when you look them up, you hit all the correct states. And again, we want to calculate our delta S naught for our reaction is equal to our product. So on our product side, we have CO2, and the coefficient there is 2. So we need to take 2 times the value that we find in that table. We're then going to subtract it from our reactant side, which we also have 2 of the COs. So we take 2 times the value of CO we would find in that table. And we would add it to our O2 value. And again, different than delta H or other things, there is actually a value that you'll find for something like O2, which would be 205. And if we do all that good stuff there, looks like perhaps we end up with minus 173.6 joules. Truthfully, in terms of units, I'll be honest with you, a lot of times the units don't necessarily cancel out very well in a lot of things that we do, but technically speaking, this would be really joules per Kelvin, because these are technically moles, right? Which would cancel out the moles part of this. And you technically still have joules per Kelvin. Most people will probably just put joules at the end of that. And for me, it's okay. If you put the Kelvin, it's fine. Technically, the moles here would obviously cancel out in that particular case. Any questions on that calculation? Now, this number that we got, and if we think about the actual reaction that we're looking at, we can sort of make a prediction. And actually, we could have made a prediction before we actually did the calculation. And we could basically see if our number really does make sense or not. So we got a negative value for delta S. And a negative value for delta S means that the entropy for that system is decreasing, which means we are going from a state of more disorder to a state of more order, right? So the order is increasing, and that means that our delta S would be negative. So if we just simply look at the equation that we got going on there, we can make a pretty safe prediction to see if our calculation was right. And what we see when we look at the actual equation is on the reactant side, we started with 3 gas molecules. Basically 2 COs and 1 O2. On the product side, we actually ended up with 2 gas molecules. And remember that the product side is sort of our final state. The reactant side is our initial state. So we ended up with less gas molecules. So just visually, if you think about it, if you got 3 gas molecules flying around your face, and then you end up with just 2 gas molecules flying around your face, you've obviously increased the amount of order. There's not as much disorder and craziness happening because you lowered the number of gas molecules. So believe it or not, before you even did the calculation, just simply looking at the equation, you could have predicted that the delta S value should have been negative for this reaction, because we're going from a place of 3 gas molecules flying around to just 2 gas molecules flying around. We're technically increasing the order. Any questions on that? And that's what we see here. If a reaction produces or consumes gases, since gas is a pretty big measure of disorder, right? So the more gases you have flying around, the more craziness you have going around, the more disorder you have around. So if a reaction produces more gases than it consumes, so that would be the opposite of what we just saw. If the products ended up with more gases than you started with, you have now put more gases out there flying around and going crazy. You have increased the disorder in that particular case, and the delta S would be predicted for the reaction to be positive. if the gas number molecules diminishes like we saw in the previous example, so on the product side, we actually have less gas molecules than what we started with, we would expect, as we saw in that calculation, that the delta S of the reaction is going to be negative. If there's really no change, which could occur, right? You could have the same number of gas molecules on each side. Then delta S may be positive or negative, but it probably will be a small number since there's not much going on in terms of changing. So take a moment here and predict what you think the sign of the reaction would be for the entropy change here for this reaction. Do you think it should be positive? Do you think it should be negative? So take a second there and think about it. All right, so when we look at this, and again, without having to go look anything up, and these are oftentimes a lot of type of questions that you come across in a thermodynamic chapter. They oftentimes will not give you any numbers, tell you not to calculate anything, just really tell you to look at the equation, and maybe they may say, hey, this is positive, this value is positive, this value is negative. What do you think is going to happen? So if we look at this, we don't need any values here. What we see on the reactant side is one gas molecule. This guy, by the way, that's a solid. And on the product side, we have no gas molecules. Again, that is also a solid. So we're going from one gas molecule down to absolutely none. So you can just visualize it, one flying around to like nothing there flying around. So obviously we went from disorder to order, more order, and we would expect, again, in this case, the delta S to be negative, like what we have here. Now, this delta S being negative is for the system and the reaction. Be very clear here, you cannot, at this point, just looking at the delta S of the system or the reaction, make a determination about spontaneity. So I have no idea at this point if this reaction or even the previous reaction is a spontaneous reaction or not. But what I do know is in terms of entropy, in terms of the amount of disorder in this one, and I believe the last one as well, we are increasing the amount of order and the entropy value is coming down. So you can't use separately the reaction or the system's entropy value to determine whether or not the reaction is spontaneous. Remember, you have to use that universe. But calculating the delta S of the system is one part of figuring out the delta S of the universe. So now let's talk about what the other part is. And so since this covers the system, let's talk about what happens for the surroundings. So we're going to talk about what happens for the delta S of the surroundings now. And this is related, and there is some relationship between the actual reaction that's happening in the system and delta H, the enthalpy. So in an exothermic process, what that means is this system, as we see here, would be giving off heat and energy to the surroundings. So what's going to happen when that reaction is exothermic and it releases all that heat and energy to the surroundings, everybody in the surroundings will now pick up all that heat and energy. And that's going to make them, obviously, if you pick up heat and energy, start to move around a lot faster, right? And that's going to create a lot more disorder in the surroundings. And in that situation, as you can see here, we would expect the surroundings entropy value to increase. And that means that the delta S of the surroundings would be a positive number in that particular example. Now, the opposite is true here. If the reaction is endothermic, which is what happens here, that means all that heat and energy is going to come from the surroundings into the system, which means when we talk about our surroundings has now lost all that heat and energy, which means everybody in the surroundings, think about it this way, you can lose some energy, kind of slow down, right? Not moving around as crazy, right? So going to kind of slow down. A lot more order is going to happen in this case. And because the amount of order will increase, the surroundings entropy will decrease. And we would expect the delta S of the surroundings to be negative in this case. So the relationship that we see is the delta S of the surroundings is proportional. That's what that little symbol is supposed to be, a proportional type symbol. Kind of looks like a bad alpha symbol, but a proportional symbol to minus delta H of the system. So let's just mathematically maybe look at this and see what that means. So if we take our values, our delta H value and our delta S value, and for an exothermic process and an endothermic, and if we think about this relationship that the delta S of the surroundings is equal to basically minus the delta H of the reaction. If I have an exothermic reaction, the delta H value should be negative. A negative delta H and a negative would give me a positive delta S, right? So minus delta H, so a minus and a minus give me a positive when you put it in there. Now, if I have an endothermic reaction, the delta H will be a positive value. So if I put this in here, minus delta H, a negative and a positive gives me a negative value for our delta S. So whether or not the reaction is exothermic or endothermic has an effect on the actual surroundings entropy. Any questions on that relationship there? But now let's talk about another factor that can really affect this sort of relationship, and that is actually the temperature of the surroundings to begin with. Now, the temperature of the surroundings to begin with does play a pretty big role in whether or not you will sort of see this sort of change. So what do I mean by that? I mean, let's take the first case here as an example, our exothermic reaction. So under normal conditions, regular temperature, like 25 degrees Celsius, everybody's favorite temperature there. Under 25 degrees Celsius, the surrounding temperatures is not that hot, right? It's not that high. It's kind of room temperature-ish. So when this reaction is exothermic and it gives off all that heat and energy to the surroundings, the amount of heat and energy that's being absorbed by the surroundings is significant to cause a pretty good jump in terms of the disorder that's going to happen. Now, let's take a look at a different example. Same situation, but instead of my surrounding temperatures being, say, 25 degrees, let's just pick 600 degrees Celsius, for example. That is significantly higher in temperature to begin with. So let's just say our surroundings were 600 degrees to begin with. Now, if my reaction happens and my exothermic reaction happens, all that heat and energy is still going to be transferred to the surroundings. But the effect that it's going to have on the entropy of the surroundings is going to be very minimal, because at probably 600 degrees Celsius to begin with, everybody in the surroundings is going crazy to begin with. So that little bit of extra heat coming from the reaction probably not going to make that tremendous amount of difference, as opposed to under like room temperature where they're kind of moving and then they gain that energy and then they start to spin a lot faster. So it's kind of like an example, for example, maybe not the best example here, but if you lit a match, and if you lit a match and you carefully put your hand near the match, you could feel the heat coming off of it. Don't burn yourself. Don't try this at home. Please don't play with fire. I think that's all the warnings I need to give, right? So if you do that and you put your hand near the match, you know, in room temperature, you'll feel the heat. But now if you take the same match, and definitely don't do this either, and you put it in, say, your oven that's been turned on to, you know, 550 degrees, you know, in terms of the temperature setting, and you take that one match and kind of put it in the oven and then sort of feel my guess is you're probably going to feel all the heat from the oven mainly, maybe a little extra heat if you got close to the match. But in that sort of setting, the energy that's coming off from the little match there is not going to add that much more heat and energy and cause that much more disturbance to that higher temperature surrounding than it would in a lower temperature surrounding. Again, don't play with matches. Don't put your hands in ovens while it's on. Please use the proper equipment. So as I was talking about right there, the change in entropy for a given amount of heat absorbed, it really does depend on the temperature of the surroundings. Again, under sort of normal conditions, an exothermic reaction, that heat and energy is going to have sort of a bigger effect, if you will, on the entropy value than if the temperature already was pretty high to begin with, because at a pretty high temperature to begin with, we're already going to have a pretty high entropy value. And again, any of that added energy not going to probably make a tremendous amount of difference. So because the entropy of the surroundings is related to the enthalpy of the reaction, to calculate the delta S of the surroundings, we take minus the delta H of the reaction or the system divided by our temperature. And our temperature does need to be in Kelvin here. Yeah. So to calculate the delta S of the surroundings, minus the delta H of the system or the reaction, divided by the temperature in Kelvin, and that will give you your delta S of the surroundings. So to calculate our delta S of the system, it is our delta S of our products minus the delta S of our reactants. And these are the two things that if we add together will allow us to get our delta S of our universe that we could use to determine whether or not a reaction would be spontaneous. Any questions on that? All right, so why don't you try that? So here we want to calculate the delta S of the system, the delta S of the surroundings for the synthesis of ammonia. And there's the delta H for that, and those would be the delta S values you can find in the table on the bottom. So calculate both of those and then decide based on what you calculated, is this reaction going to be spontaneous or non-spontaneous? So take a couple minutes and see what you come up with. Okay, so let's see how we're doing. So we want to calculate a couple of things here. We want to calculate the delta S of the system and the delta S of the surroundings. And again, to do our system, we're going to go to our table, look up the values, which is what these are. These are basically delta S, not on these guys. And to do that, we will take our delta S would be our products. So we have 2 of our NH3. So that was 193 each. And that's going to take care of everybody on the product side, minus our reactant side. So we have 1 and 2, which is 192. Plus our other guy, which is 3 of our H2, which is 131. And if we do all that here, let's see. 2 times 193 minus 192 plus 3 times 131. Looks like for our delta S of our reaction here, which technically would probably be that, is minus 199 joules. Again, you could keep the Kelvin there if you want. Again, the moles would most likely cancel out. Now, we do end up with a negative number here for our delta S of our reaction. And again, we could see if that does make sense based on the reaction. And based on the reaction here, we have 4 gas molecules. And we're ending up with 2 gas molecules. So again, we're going from a situation of 4 things flying around to only 2 things flying around. So we're increasing the order. And we would expect, like we've been talking about, that our delta S for our reaction or our system is negative 199, and a negative number telling us that the entropy value is decreasing because the amount of order is increasing. Any questions on that so far? Now, we also want to calculate our delta S of our surroundings, and that has to do with the relationship of our minus delta H of the reaction divided by our temperature that needs to be in Kelvin. So 25 is 298 Kelvin. And I'm going to put this in. That's going to give us minus 92.6. I'm going to multiply this by 1,000 to convert it to joules. You don't have to, but I'm going to do that because I'm going to need it in joules perhaps in just a second. And I'm going to divide it by 298 Kelvin in this case. And for our system here, our surroundings, we end up with we'll call it 311 joules in this case for the delta S of our surroundings. Also makes sense based on what we just talked about. Here, the temperature is only 25 degrees. This is an exothermic reaction, which means heat and energy is going into the surroundings, causing the surroundings to gain all that heat and energy and causing a lot more disorder in the surroundings. And we would expect it, as you can see here, for the surroundings to be a positive number to indicate that we are increasing the amount of entropy. So now that we have our system and we have our surroundings, and again, this is why I did convert it into joules, because to calculate the delta S of the universe, I need to basically add those together, minus 199 joules plus 311 joules. Now, at this point, if you left it in kilojoules, you're over here at 0.311, right? So you're going to run into some trouble here if you don't convert them to the same units. So again, that's why I sort of did the conversion up here, so I didn't have to do it later. But you could do it later, or you could convert this to kilojoules, I suppose, if you wanted to. So we're looking at something like, what we got there, about 112, and The units are joules here. A reminder that as we talked about, delta S is typically given in joules, which means also why you might want to convert it to joules instead of kilojoules on the other one. So that's 3 numbers. So what does all these numbers mean? So we talked about the 2 individual numbers, that they both make sense, that the reaction is producing less gas molecules than it started with. So our delta S for the reaction should be negative as it's becoming more ordered. The surroundings is gaining that energy under sort of regular temperature conditions, which means should cause an increase in the disorder in the surroundings, which is why our number is positive. And now we finally can add them together and use our delta S of the universe to determine whether or not this reaction is spontaneous. And what we see is the delta S of the universe is a positive number. And because the delta S of the universe is positive, it is going to be a spontaneous process. And what does that mean? It means that basically this reaction will head towards the product side because it should occur. Now, does this reaction occur super fast? The answer is no. They typically need to use a catalyst in this reaction to have it occur a lot faster. But under normal conditions, even though it doesn't necessarily occur super fast, it will eventually occur and will happen because it is spontaneous. Any questions on any parts of that there? So again, individually, delta S of the reaction, delta S of the surroundings, you could kind of use them to figure out what's going on for the reaction, or the system and the surroundings. But again, you do need to sort of combo them together to make sort of that judgment overall in terms of the reaction. Any questions on any of that there? So that brings us to sort of the third law of thermodynamics, which is basically the entropy of a perfect crystalline substance is 0 at absolute 0 temperature. So obviously, if you have a perfect crystalline substance, that's like your ionic substances, all perfectly ordered. Perhaps you remember things like cubic unit cells and perfectly orderedness of all that kind of stuff. But obviously, to get something that's perfect, kind of like one way to be perfect, if you will, which is why when we look back to our Boltzmann equation here, kind of only one way to do that. Natural log of 1 is 0, which means the entropy value is very, very low. We do see here in this graph sort of what we talked about, that the entropy increases as you go from different states. So obviously in the solid state, as you can see in that picture, everything is very, very ordered. In the liquid state, as we've been talking about, there's a little bit more room for movement. So obviously that movement is going to cause more disorder and the entropy increases until we get to the gas phase there, and the entropy value obviously also increases. We also see these flat lines, which you might be familiar with when you talked about enthalpy. These are our plateaus that occur, right, at our kind of upside downish, but here is our temperature. So for example, if this was water or something, right, this would be 100 degrees Celsius, the normal boiling point. If this was water, this would be 0 degrees Celsius, the normal freezing point. As you know, phase changes occur right there, flat, right? And you may be more familiar with this in terms of energy and temperature. Looks like this type of curve. Again, to do that transition, say, between solid, liquid, and gas, that transition, again, if it was, say, it was something like water, would be 0 degrees Celsius. At exactly 0 degrees Celsius, right, you still have solid and liquid in equilibrium with each other. And at 100 degrees Celsius, which would be over here, you also still have equilibrium between liquid and gas that's occurring. So there's also the entropy for those phases. If you remember the heat to do those transition, this is like your heat of fusion. This is your heat of vaporization up here. There's also, as we'll talk about, the entropy of fusion and the entropy of vaporization as well. Any questions on that? And we'll get a little bit more into that in just a little bit. So let's talk about another sort of thermodynamic value, which is very helpful as well. And this is what is known as Gibbs free energy. And Gibbs free energy lets us use a different letter. Thank goodness as well. We got to S. Hey, we got to use G as well. So delta G is Gibbs free energy. And the name basically implies what it does or what it is. Free energy. So we're talking about free energy that's available to do usually some type of work on something, or work could be done on something else, depending on which way that's sort of flowing. So just now we talked about the delta S of our universe. And again, if you have a positive number for the delta S of the universe, it's a spontaneous process. And obviously, if you have the opposite of that, which would be a negative number for your universe, it would be a non-spontaneous process. We can actually use delta G, our Gibbs free energy, to calculate whether or not a reaction will be spontaneous by just actually calculating the delta G value. And there actually is, as we will see in this chapter, like 3 different ways you could sort of calculate delta G. And one way is what this formula here. And we'll talk about a couple other ways as we go through this chapter here. But delta G, which is Gibbs free energy, or just sometimes called free energy, is equal to delta S of the system or the reaction. So that's our enthalpy, minus T, which is our temperature in Kelvin, and delta S, which is our entropy. Now, units, this is definitely another equation where you want to watch units. Delta H values are typically in kilojoules. Delta S values, as we've seen, are typically in joules. So again, if you use this equation and you decide not to change the units, you are obviously going to be off by a factor of like 1,000. So it really doesn't matter in this case. You could convert them both to joules and then convert to kilojoules at the end. You could convert everybody to kilojoules and you'll be fine. So in terms of units, delta G typically is given in kilojoules. So just a refresh of units, delta H is also typically kilojoules. So the one value that typically is not given in kilojoules is delta S. That is typically given in joules. So technically speaking, if they don't really specify what unit to use, you could use any unit you want. But traditionally speaking, delta G, delta H usually are given in kilojoules, and delta S is usually given in joules. So we can calculate delta G, and then again, this is one way in which you could do that. And if you calculate delta G and it's less than 0, that means that it's negative. Right? The reaction will be spontaneous exactly how it's written in the forward direction. So here we could just calculate delta G, and again, if it's positive or negative, it will allow us to determine whether or not this reaction will be spontaneous. If delta G is positive, the reaction is going to be non-spontaneous the way it is written, which means the reaction, the way it's written, will not occur. But if you flip the reaction around, that would make the delta G value go from positive to negative. And that's what the second part of that sentence is basically saying. The reaction is non-spontaneous as it is written, but if you reverse the reaction, it will become spontaneous. And that is because, again, another way that you can calculate delta G is to take the delta G of the products minus the delta G of the reactants, as we will see. And those would be table values you would find. Those are G's. They kind of look like 6s, but they're actually G's. You could calculate it just like we did for delta S, just like you do for delta H. And the reason why this happens, right, is if you calculated this and you got a positive value, if you reverse the reactions, or if you reverse the reaction, your products become your reactants become your products, and that means that these numbers would reverse as well, and that would lead you most likely to a negative value for delta G if you reverse the reaction. So sometimes you'll see that kind of weird wording, like it's not spontaneous the way it's written, but the reverse reaction is spontaneous. And again, that's what they're sort of talking about. If you are at equilibrium, the delta G value will be 0 in that particular case. So those are 2 ways you can calculate delta G. I usually tell people, they sometimes ask, which way should I do it? And truthful answer is, based on the information given to you, that's probably the best way to choose how to calculate delta G. So what that means, just from these two ways to calculate delta G, if you have a problem where they give you the delta H value and they give you the delta S value, then I would probably go with, obviously, this equation here. If you're just given the chemical equation and no other piece of information, I would probably go to a table and calculate the delta G using products minus reactants. So, you'll come across some problems where you're like, well, I know a couple of different ways, or 2 or 3 different ways to calculate delta G, which way would be the best? And really, probably the best way is, like I just said, sort of based on the information that's provided to you, I would choose the most appropriate sort of way to calculate it based on what's given to you, or maybe what's not given to you. So as I sort of jumped the gun here, but a much prettier looking G than what I wrote is here. This again is another way that you could calculate the delta G. Again, that little knot on there basically means table conditions, standard conditions. And usually what that means is, like I said, you go to a table, you look up your delta G values. And again, we're going to take our products, which is our final state, minus our reactants, which is our initial state, just like we did for delta H before, just like we did for delta S. We are going to take the coefficients into account and multiply each of the values, obviously, by the moles that are there when we look it up in the table. Same sort of precautions that you should be aware of as you look up these values, just like everybody else's. You want to make sure, A, you find what you're looking for, and B, that you find it in the correct state. Delta G, again, in the table will typically be in kilojoules, and also delta G, just like delta H, for things that are in their standard state, like O2, N2, metal by itself. Those guys, again, here for delta G, will actually go back to 0. So for delta H and delta G, you will have 0 for things that are in their natural state. For delta S is the only one where you will actually have some values given for those things. And these are sometimes referred to as the delta G of formation, and that's basically the table value that you look up is what that little F stands for. So when you look it up in the table, those are the standard free energy of formation, and that's basically the energy change that occurs when 1 mole of the compound is basically formed, and that's what the little F stands for, is formation. I think I talked about this a little bit earlier, but again, in this table, not from your book, but you do have a similar one, I think, in there as well. Those are sort of what we consider standard conditions. And the main 3 usually are, as I mentioned, if you're dealing with any type of gases, everybody's at 1 atmosphere. If you're dealing with concentration, everybody's at 1 molar. And typically the temperature in pretty much every table that you look up usually is 25 degrees. So those are sort of the standard conditions. And then again, is sort of what the little knot represents is, this is measured under these sort of ideal conditions, standard conditions. This is what those values would be. All right, so why don't you try this one here. Calculate the standard free energy change for the following reaction. Values are there on the bottom, so see what you come up with. Those would be the values you would be able to find, obviously, in a table. So take a minute or 2 here and see what you come up with. Okay, so let's take a look here. So again, in this situation, like I was mentioning before, we've already kind of seen a couple different equations that you could use to calculate the delta G. And again, in this case, if you're just given the reaction like we were here, and pretty much you might not be given any other information, that usually will tell you that you should go find that thermodynamic table that you can find in the back of your book or somewhere else and look up these values. And again, here we're going to use the delta G equals the delta G of our products minus the delta G of our reactants. And again, we want to make sure we do take into account the coefficients that we see there. So on our product side, we have 12 CO2s and looks like it's minus 394.4 kilojoules. We're going to add it to 6 times the value for water, which down here, we'll go with this number here, minus 237.2. And that takes care of all of our product side. We're then going to subtract it from our reactant side, which was our initial set of conditions. And that's going to be 2 times our C6H6, which is benzene. Looks like it's over here, 124.5. And minus 15 times O2. I don't see O2 here, but again, this is a reminder that O2 is going to be 0 because it is in a standard state. So that's basically 15 times 0 kilojoules. So if you look it up on a real thermodynamic table, it will say 0 there. If you look it up on a table I make, it probably will still say 0. But if in case you can't find it, that usually means 0, by the way, but it probably will be up there. So just keep that in mind if you're using a thermodynamic table maybe that I made and it's not up there. Sometimes for space purposes, basically you could probably safely use 0, but I probably will put them up there just to make sure. If I do this correctly, hopefully, 2 times 124.5. All right, so I think I punched it in correctly. Hopefully you did as well. And if I didn't, please let me know. Let me see here. So on my calculator, minus 6405 kilojoules, I hope. Anybody else get that? I hope. Let me double check real quick. I feel like I hit some wrong numbers here. That looks good, I think. Perfect. All right, so minus 6405 kilojoules. So we calculate our delta G here, which is negative, and that should tell us that this reaction is going to be spontaneous. Yeah. So this is going to be spontaneous. The delta G is negative. So again, unlike necessarily the entropy value, we can use our free energy to indicate whether or not it is going to be a spontaneous reaction or not. So again, if you calculate delta G and it's a positive number, non-spontaneous. If you calculate delta G and it's a negative number, it will be spontaneous. So what that means is this reaction should proceed from reactants to products the way it's written. And you might imagine that you would expect that since this looks like a combustion reaction, and usually those do sort of occur pretty easily, right? All right, any questions on that calculation first off? So let's talk about this actual formula or the other formula that we saw here that you could calculate delta G. And we can actually look at this formula and sort of make some determinations as to whether or not we would predict the reaction being spontaneous or being non-spontaneous. And like I said before, out of probably all the chapters that you'll come across in this book, this chapter will probably have the most type of questions sort of like this. And what I mean by that is a lot of times they will just sort of not give you information. They'll just say, not information like numbers, for example. They may just say, hey, the delta H is positive, the delta S is negative. Do you expect this reaction to be spontaneous or non-spontaneous? So let's talk about how we could use this other equation here to sort of figure those things out. So if we have our delta H and our delta S in this case, and delta G. I'll work on my G's. They really look like sixes. So let's talk about what happens if our delta H is a positive number and our delta S is also a positive number. So if this is a positive number and this is a positive number, what does that necessarily mean? So that would put us in this box here where delta H is positive, delta S is positive. That means that this guy is going to be positive and this one will be positive, which means the back end here will be negative. But this is where units come into play, and it's important because delta H is in kilojoules and delta S is in joules, which means to start off with, our delta H is 1,000-fold probably higher than our delta S to begin with, which means under normal conditions or low conditions where this temperature value is low, the back end here will always be smaller than the front end, which means under sort of low temperatures, like it says here, we would expect the delta G to be a positive number under sort of low temp conditions. Now, it would become a negative number if we could get a sufficiently high temperature to happen here, a high enough temperature to make the back part become a larger number than the front part. And at high temperatures, delta G would become negative and spontaneous. So if you have a positive H and a positive S, if you're under sort of normal conditions in terms of temperature, you would expect that reaction probably to be non-spontaneous the way it's written. If you're under positive H and positive S and you're at high temperature, a high enough temperature to get the back part larger than the front part of that formula, then you would expect it to be spontaneous. What happens if our delta H is negative and our delta S is positive? In this case, this guy would be negative, this guy would be positive, and most likely our temperature is going to be positive, which means no matter what happens, we have a negative number here, we have a negative number here, which means no matter what the situation is in terms of temperature, we would expect a delta G to always be negative and spontaneous at any temperature, because there's no way for you to get a positive number basically in that case. Now, what would happen if our delta H was positive here and negative delta S? That means that in that case, this is going to be positive. The negative delta S here and the subtract part of it here will turn this back part into a positive number, which means in that situation, you're going to end up with a positive value for delta G at any temperature. So the two situations where no matter what you do in terms of temperature, that the delta G will definitely be either negative or positive are these two situations here. You have a delta H that's negative and a delta S that's positive. Going to always give you a negative delta G at any temperature. If you have a delta H that's positive and a delta S that's negative, going to give you a positive value for delta G at any temperature and will be non-spontaneous. So your last combination there is this box here, which is a negative delta H and a negative delta S. So in that case, we have a negative value here and a negative value here. So this negative value is going to turn this back part into a positive, which again means because this is in joules and this is in kilojoules, you need a very high temperature in order for this guy to overtake the negative part of it. So at high temperatures, you would have a positive delta G. And at low temperatures, this part was not going to be able to overtake the negative part, and you would have a negative value at low temp. So these are some very common sort of questions that you can be asked in this chapter. You don't have to do calculations. You can actually put numbers in to kind of, if you wanted to. But this is also a good thing to think about as you are doing calculations, because again, you can sort of predict what you expect to happen, so before you do the calculations. So let's take a look at this right here. And this reaction here has a delta H value of 177.8 and a delta S value of 160.5. So why don't you first calculate the delta G naught for this reaction here, using that information, at 25 degrees Celsius. So what is the delta G naught at 25 degrees Celsius? And predict if it is going to be spontaneous. So take a minute or so and calculate that, see what you come up with. Okay, so since we're getting to the end, let's take a look. So again, in this situation, we're looking for the delta G. We're given the H value and the S value. So as I mentioned before, probably best to use the equation that has those in it, which would be our delta H minus our T delta S. So in this case, we could just plug and chug into there. So our delta H is 177. I'm going to go 177.8, and I'm going to times it by 1,000, and that's going to convert it to joules. And again, I'm doing that because my S is in joules, and just makes it easier. You could convert the S into kilojoules if you wanted to. We're going to go minus our temperature that does need to be converted to Kelvin, which is 298. And because I converted my other guy into joules, I could just use this the way it is and run onto the graph there. And if I do all that, 177.8 times 1,000 minus 298 times 160.5 gets me a lot of numbers. 129,971 joules. Kind of clean it up a little bit to about 130 kilojoules. Again, delta G typically given in kilojoules. So what this does tell us, though, is our delta G here is a positive number at 25 degrees Celsius, which means at 25 degrees Celsius, this is a non-spontaneous reaction, as we can see here. Any questions first off on that calculation? Now, when we look at this reaction, we see that under sort of standard temperature there at 25 degrees, it's not going to be spontaneous. Could we figure out at what temperature it does become spontaneous? And we can by actually using the same formula. So if we take the same formula here, delta G equals delta H minus T delta S. What we know, in order for this reaction to become spontaneous, delta G needs to be negative, and negative values happen right after 0, right? So we could set delta G equal to 0, and that would give us delta H minus T delta S. And if I rearrange and solve, T delta S equals delta H, which means T equals delta H divided by delta S. And when I put my numbers into here, again, I do need to get the units the same. So I'm going to do the same thing. I'm going to take 177.8 times 1,000 to convert it to joules, divided by my delta S, which is 160.5 joules per Kelvin. This is where my Kelvin comes into play. And we get 177.8 times 1,000 divided by 160.5 gives me something like 1108 Kelvin. And what this temperature represents is the minimum temperature at which this reaction becomes spontaneous. If I want Celsius and I subtract 273 from it, I get 835 degrees Celsius, which I guess is good. I'm writing on the graph here because looky at that number right there. That is 835 degrees Celsius. 835 degrees Celsius is the minimum temperature at which this reaction actually becomes spontaneous. How do we know that from the graph? If we look at the graph, we are graphing the pressure of CO2 on the Y, temperature in degrees Celsius on the X. The only thing that's a gas in this entire reaction is CO2, which means the only way we could actually get pressure to occur in this reaction is this reaction needs to go this way and start producing some CO2. And you can see in this graph, we really don't get to standard pressure conditions of 1 atmosphere until about 835 degrees Celsius. You can see that it does start a little bit before that, but it doesn't reach that level of 1 atmosphere until about 835 degrees Celsius. And that is, again, considered sort of the minimum temperature at which this reaction would turn spontaneous. So this equation as well, it's helpful to determine, is this reaction spontaneous? And if it's not spontaneous at that particular temperature, you can actually use it to determine what temperature it will become spontaneous, as we just did there, 835 degrees Celsius. Any questions on that there? And just a last sort of point to tie it together with what we were talking about just a second ago. When we look at our delta H and our delta S values, they are both positive values. And if you remember from what we were talking about earlier, in that equation of G equals H minus T delta S, when this is positive and this is positive, in order for this back part of the number to become more negative than the positive part, you need a very high temperature. And I would say 835 degrees is definitely a high temperature, as opposed to a regular temperature like 25 degrees where it was not spontaneous. So again, that ties together what we were just talking about in terms of positive sort of effect. Any questions on that? Okay, so we will stop there for lecture today. A reminder that, again, we do have the exam tomorrow. The exam is on those 3 chapters. What's that, 15, 16, and 19. So buffers, titrations, KSP, and nuclear chemistry, and also a reminder, salts from the previous exam, and also polyprotic acids and stuff like that. Any questions on that? Today we are doing experiment 12, I think. Yes. So experiment 12, there was no pre-lab because, I didn't figure out where it was. So we didn't actually do it. We don't usually do this experiment in the summer, but since the 4th of July fell on a weekend this time, we didn't actually lose a day. So we're going to do experiment 12 today. So we'll do it like normal. You'll watch the video, you'll work it out and all that good stuff. And that also means, like I said the other day, I think the online homework should be due soon. So make sure that you do take care of that as well. So since we ran a little long here today, why don't we stretch your legs and all that good stuff? So why don't we do like a 3:15, we'll start lab, okay? So I'll see everybody at 3:15, get up, stretch. I'm gonna try to stand and walk around for a bit. And we'll be back together in just a bit. Make sure you type here if you haven't done so already. Again, about 3:15, we'll start lab, okay?